All right, we're going to look at graphs of polar equations. So make sure you have your calculator out with you because there's a few things I'm going to show you on how to do some of these in the calculator. So the first thing we're going to look at is how to graph them by hand. And so I know this picture isn't the best, but it's also in your book. So the first graph we're going to look at is r equals cosine of theta. And in your calculator, you've been able to type in y equals equations, but this is not what that is. This is an r equals, so don't try to go in and type in y equals cosine theta. You know what that's going to give you. It's going to look like this, and that's not the same because this is in polar coordinates, not in Cartesian coordinates, okay? So we can use the information that we know about the unit circle. So we're going to start with theta, and when theta is 0, cosine of 0 is 1. So at 0, we'd start at 1. And then we go pi over 6 is 0.9. So at pi over 6, by the way, this is 1, it's 0.9. And then at pi over 3, it's 0.5. We keep going around. At pi over 2, we're back here at 0. Sorry, 0 is 1 out here. And then at 2 pi over 3, which would be this line, we're at negative 0.5, so we have to come back the other way. And 5 pi over 6, right here, we're back here, you're at negative 0.9, and at pi, we'd be at negative 1, and it's just going to go back around. So this is our graph of r equals cosine theta. So we're still using your unit circle points, and we're graphing those on a polar axis. Now let's walk through putting the points on this one together, okay? So this is for r equals 3 sine of theta, okay? And this is theta, and then here is the normal r's, okay? So 3 sine of theta, we'll go ahead and make this a 1, this is 2, and this is 3. So you've got to make sure you take and scale it properly. So if this is what r would typically be for sine, we need to then multiply it by 3. So this is still 0. So 0, 0. And then at pi over 6, it would be 0.5 times 3. So that would be a 1.5. So at pi over 6, we need to go to 1.5. And pi over 3, 0.9 times 3 would be 2.7. 2.7 about here. Remember, I'm at pi over 3, okay? And then at pi over 2, 1 times 3 is 3. So I need to go to 3. 2.7 again at 2 pi over 3. That did not graph well for some reason. I think I know why. I think I was accidentally, yeah, my hand was on the side of the screen. So at 5 pi over 6, we're at 1.5. Oh, do you guys see that circle? I do. And then at 0, we're back at 0. At negative, at 7 pi over 6, we're at negative 1.5. So 7 pi over 6, negative 1.5 is back here. So it's going to loop back around. So right here is 3 sine of theta. Okay, so I was looking at that going, this doesn't look like a circle to me. Hopefully you guys saw that I went out way too far. 3's right here. Now that looks like a circle. It's like, that looks like an oval. It should have been a circle. So a little bit about symmetry on polar graphs. You can have symmetry in 3 different ways. You could have symmetry with respect to pi over 2. And so it's equal distance on both sides of this pi over 2. Reflects over that. it could be about the polar axis. This is our polar axis again. Equal distance both ways here. Again, if you fold it over that line, it would match up. And then the last one that we have is with respect to the pole. Okay, and it's equal distance back and forth both ways here. It's 180 degrees or pi apart. So another way, just making sure that you're aware of this, is that if you plug in points into the equation. For example, so just so you're aware, if something I say on here is a little weird, be aware that, remember, while I'm making this video, this is during the quarantine time. My kids are homeschooled and they keep interrupting me. So, just in case, because I have no idea what I just said. But I'm looking at these things and I'm thinking I need to talk about symmetry if you plug into the equations, I think. So, what's going to happen is that if you don't want to go and graph it and look at it, which is one way to do it. So, for example, if I have r theta, if I plug r negative theta back in, it's going to give me the same thing. If I plug in a negative theta, it's still going to give me the same r. So if I plug in theta and it gives me r, I plug in negative theta, it will still give me an r. I could also plug in pi minus theta, and pi minus theta will give me a negative r. So that's what these are talking about. So if I look back over here at this one, and in a second it's going to make a little bit more sense why. We're going to talk about something else. So r theta, if I plug in a pi minus theta, it will give me an r, not a negative r, but an r. If it's symmetrical with respect to the line, theta equals pi over 2. And then if I plug in a negative theta, it would give me a negative r. Alright, so we're going to use symmetry to graph this equation, 1 minus 2 cosine of theta. So if I plug in a negative theta, I'm going to start there. I need to see what it's going to give me out. If it gives me out an r back, then I know it's symmetric with respect to the pole. If it comes out to be a negative r, I know it's going to be symmetrical with respect to the line of pi over 2. So 1 minus 2 cosine of negative theta. And with our even and odd functions, cosine, if I plug in a negative, it's going to give me back out just a positive. So this one, since it gave me back out the same r, it's going to be symmetrical with respect to the polar axis. So I only need to graph from 0 to pi, that interval, because it's going to be symmetrical with respect to that. So let's plot some points. So let's do our scaling. So we're going to call this a 1, a 2, 3, 4, and a 5. Okay. Make sure you know what your scales are, of course. And I wrote it that way. I could have written it on the other side. And so at 0, we're at -1. So we're back here. This is, remember, you got to be careful about negatives. Negatives is the direction. Okay, I guess I should have 1, 2, 3, 4, 5, because we're over on this side. That's the positive side. And then at pi over 6, I'm at -0.7. So down here, at pi over 4, I'm at -0.4. At pi over 3, it's 0. At pi over 2, I'm out at 1. At 2 pi over 3, I'm out at 2. And all I'm just plugging these in and simplifying. You can use your unit circle to figure out the values. You can use a chart and just make sure. Okay, 2 here, sorry. At 3 pi over 4, I'm at 2.4. 1, 2.4. At 5 pi over 6, I'm at 2.7. And then at pi, I'm at 3. Now, symmetry says that it's going to repeat itself on the other side. So I'm just going to use symmetry to go through and plot I think I just messed that up. Yeah, a little bit there. So it's easy to do. Sorry, guys. Hopefully you'll be a little better at this than me. And you're like, oh no. There we go. That's still not quite in the right spot, that one. Maybe because I need the other one out farther. Yeah, that helps. And then back down at 1, 0. I'm just following the different lines here around is what I'm doing. I'm just this line, this line, this line here matches back to 0. And then when I'm on this heavy black line, I need to be over on the other side with it. And then my last one would be here. And I'm just following the points around. Now, to graph, follow around where you were at. So at 0, it started at -1, and it went like this. And then symmetry says it's going to come back around. And that's the shape. So I didn't have to do all of my points from 0 to 2 pi. I was able to stop and use the symmetry, knowing that it's going to continue to do a reflected image to finish it out. So this will help a little bit more. I like this test better than the other one. So some quick tests for symmetry and polar graphs. If it's a cosine function, it's going to be symmetrical with respect to the polar axis, which is what we just found out. We just did a cosine, and it was symmetrical with respect to the polar axis here. Now, if it's a sine function, it's going to be symmetrical about the line pi over 2. So it will be symmetrical about pi over 2. So 3 plus the sine of theta is symmetrical with respect to the line of pi over 2. So this is your x, y axes. So back to, well, how about I erase all that? If I were to draw an xy axis and look back at my unit circle, I'm not going to draw all of my numbers out. The reason that cosine is symmetrical with respect to the polar axis is because this goes positive and then negative for the cosine values, and then negative and positive. And so it's symmetrical this way with, here's your polar axis. And then sine goes positive, positive, negative, negative. So it's symmetrical this way. And it's not the same as a polar graph, but it helps remember which one's which. So cosine is respect with polar, and sine is symmetrical with respect to pi over 2. All right, so let's look at this. Graphing these just gets a little bit, takes a little getting used to, and I'm going to show you something at the end of it to help you, but I want you to try to do it by hand, and then you can go back and check it by calculator. So first of all, let's check symmetry. This is a r equals 2 cosine of theta. So it's a cosine function, which means it's going to be symmetrical. So symmetry, S-Y-M-M-E-T, is with respect to the polar axis, which means that you only need to look at the point 0 to pi, and then you can just repeat it, because it repeats it. And then let's figure out what our zeros are going to be. So if we were going to graph this function, not an r equals, but a y equals 2 cosine of 3x on an xy coordinate plane. So we're going to graph it first on an xy coordinate plane over here on the side, and then we'll go through and we'll graph it on, using that, we'll graph it on a polar coordinate plane. So your max value, because cosine of 0 is typically a 1, so it's going to be a 2 because we multiply it out. This will be a pi over 2 in the middle here. It'll be pi over 4 and 3 pi over 4. I don't really like it going all the way out to pi, but we need it because of the symmetry. We know we have to go from 0 to pi. And so be careful where things are going to fall at here. Because the period on this one is typically 2 pi, but we've got it divided by 3, so it's only going to go to 2 pi over 3. So I'm actually going to change up my lines here a little bit. I'm not going to have this one or this one. And I need to do 3s, so I'm going to put them here, ignoring the other ones. So this is going to be pi over 6, pi over 3, 2 pi over 3, and 5 pi over 6. Of course, there's pi. So I'm breaking it into the thirds for this because I want to end back up here at 2 pi over 3. And then halfway between those, that would be pi over 3. That would be my negative 2. And then it goes down. It'll come back up at 5 pi over 6. It'll be here, and then back down at pi. It'll come this way. So it'll look like this. So to graph it then on, well, a few things I can tell from this before we go, and I put a polar coordinate plane on here. I know that my max values are going to be at 2 or at a negative 2, at 0 and at 2 pi over 3 are my max values. My min then is at negative 2 at pi over 3 and at pi. So those are going to be my two min values. My zeros are going to occur going to be at pi over 6, at pi over 2, and at 5 pi over 6. Because that's where it was 0 at, right here, here, and here. Alright, now let's graph it. I'm going to use the symmetry, and then I only need to go to pi, 0 to pi, because I know it's going to be symmetrical with respect to the polar axis. So at, just using these, at 0, it's 2, so 1, 2, it's going to be here. At 2 pi over 3, it's 2. And then it's going to be negative 2 at pi over 3, so negative 2 goes back the other way. And also at pi, which brings me back to where I started, so that's good. So I've got that and this one done. Now let's do our zeros. The zeros are at pi over 6. So I would start at 2. I go to pi over 6 at 0. I'm going to go back to pi over 3, which is down here. And then at pi over 2 goes back to 0. And then at 2 pi over 3 goes back. And then 5 pi over 6, it goes back to 0. And then at pi, it goes back to 2. And then it repeats itself. So I don't need to go and do it again. So actually that's it right there. You're probably thinking, whoa, this is a lot to graph. Just hold on. Really, you can take these and then just kind of follow it through. You can also take your points and follow through. But main things you're looking for are your max and min values and your zeros. You don't care about where it really follows. And you're going to see all the shapes here in a minute, what they look like. It was actually just a second. So here are your special types of polar graphs. And they follow patterns, just like you have parent graphs for all your Cartesian coordinate systems, your XY coordinates, you have parent graphs for these. So we have circles. And the first type is r equals a cosine of theta or r equals a sine of theta. And they're just circles. Notice there is nothing between the theta. Okay, so that's a 1 there. Any other number, it is not a circle. So first thing, if a is greater than 0 on a cosine, which means it's positive, it's going to be on the positive, and it's symmetrical because it's cosine with respect to the polar. And then the next thing, how far you know that it comes out, is going to be whatever a is, that's the radius. So that's how, or actually it's the diameter, that's how far out it goes from the center there. So if this were 5, it'd come out 5 units. And then if a is negative, it's going to be on the other side for cosine. Again, going out however far a is. Now for sine, it's symmetrical with respect to pi over 2. So it is going to be either up or down. It's up if a is positive, it's down if a is negative. And of course it goes out however far a is. Alright, so what you don't know is that I just recorded, but I'm going to redo it because I need to make this page a little bit more simple for you guys. So this is a lemniscon. It's in the form a plus or minus cosine b, a plus or minus, sorry, I think I said the b in the wrong spot, a plus or minus b cosine of theta, or a plus or minus b sine of theta. First thing, let's talk about cosines and sines. If it's cosine, it's going to be a left or right. And if it's sine, it's going to be down or up. Now to know which is which, really all it has to do with is the plus or minus. If it's a minus for sine, it's going to be down. If it's a minus for cosine, it'll be to the left. And then for sine, or sorry, for cosine, a plus is to the right. And for sine, a plus, it'll mainly go up. So knowing that, you can do these shapes with a plus or a minus. It's just going to be different up, down, left, or right, depending upon sine, cosine, or plus or minus. So again, reiterating. If it's going to go down, it's going to be a minus sign. If it's going to go up, it's going to be a plus sign. If it's going to go left, it's a minus cosine. If it's going to go right, it's a plus cosine. So looking at the graphs themselves now. If it has an inner loop, it's going to be a is less than b. And notice for all of these, from your polar axis to the tip of the larger one, it's always a plus b. For some reason, and I don't know why, they said that's 2a instead of just saying, well, they're always a plus b. Because right here, this is a equals b. So it's still a plus b. So the distance from that center to the tip is always a plus b. So from the pole, so your max value is always a plus b for these. I think I reiterated that enough. And then, looking at that, how to know what it's going to be. So if it's an inner loop, a is less than b. If they're equal, it's called specifically a cardioid, so that's a specific name for those. If a is between just 1b and twice b, it's going to be a dimpled lemniscon. So it's just kind of a dimple in it. And then if it's a convex lemniscon, so notice it doesn't come in, it goes out farther here, then a is greater than or equal to twice b. Alright, the next kind is a rose, and this is actually my favorite. You'll have equations in the form a equals, sorry, not a equals. I think I'm going crazy right now. R equals, it's probably all the quarantine, cosine of n theta. Or it could be a sine of n theta. Now, if n is even, you're going to have twice the number of petals. So right here, cosine, this would be cosine of 4 theta. And so you have 8 petals. 1, 2, 3, 4, 5, 6, 7, 8. And of course it's cosine, so it's symmetrical with respect to the polar axis. And then if n is odd, you actually just have n petals. So this is a sine of 3 theta is what's graphed, and so you have 3 petals. And notice it is symmetrical because it's sine with respect to pi over 2. And so they didn't cosine that was odd. So this would be cosine of 5 theta. So there's 5 petals. And it's symmetrical with respect to your polar axis, and then sine of 2 theta. And so there's 4 petals. Now the distance from the pole to the tip of the petal is always A. So whatever A is, that's how far it goes out. Now these are our last 2 types. We have limnoscetes and spiral of Archimedes. Limnoscetes are going to always have a square. So if you look at them, you know, oh, well, that's a limnoscete because it has an r squared equals a squared. And a will be the distance from the pole to the tip of the loop. Cosine or sine of 2 theta. So don't let this 2 inside throw you. Just because it is even, it's not going to have 4 petals because this is not a rose, because there's an r squared here. So your max r value will always be the square root of this number because it's a squared, and this distance here is a. Cosines go this way, and sines go this way. And these are actually symmetrical with respect to the pole. Not the polar axis, but the pole. So that's why sines and cosines, cosine looks like it's still symmetrical with respect to the polar axis, but it's really with respect to the pole here. And same thing with sine here. You'd think, oh, well, it's not symmetrical with respect to pi over 2. That's because it's symmetrical with respect to the pole. Now, spiral of Archimedes, this is our last one. They're in the form of r equals a theta plus b theta, a theta plus b. R equals a theta plus b. Notice there's no sines, no cosines on this one. This one, there's no max r value because they continue to go. Now, if theta is greater than 0, when you're at your pole and you're starting, it's going to start up and spiral counterclockwise. And if your theta is less than 0, so negative, it's going to go down and spiral counterclockwise as well. So they spiral the same direction, just whether one starts up or one starts down. So this is written out for us. So we're going to identify the type of curve given by each equation. So I look at this has an r squared. So we know because of that, that is going to be a limnoscete. Determine its symmetry. Limnoscetes are symmetrical with respect to the pole. Our zeros are at 0, pi over 2, and 3 pi over 2. Our max value is 4. So it's the number right here. So make sure you take the square root and see what that's going to be. And that's 0 because of the sine of 2 theta there. Our second one right here is r equals 3 theta. So this is in the form of a spiral of Archimedes. This is Archimedes. It has a pi over 2 symmetry. The only zero is at 0, and they have no max values. Alright, I want to show you how to use your graphing calculator to graph these. So notice right here, I have a circle graphed. And the way that I did that is that I went and I changed my mode. So go into mode, and then go down and we want polar. So we're usually in function, which is your XY coordinate, but we want in polar. So if you go to polar and then go to y equals, you'll have an r here instead of a y equals. And so that's good. So we can type in any function we want here. So right now I have 3 sine of theta. And this button right here is still, or sorry, 3 sine. Yeah, I said sine. This is your x, t, theta, and n is what it says. So you can use any of these. And then also, one thing to let you know is that my mode, I changed it back to radians. Because if it's in degrees, that's 360 degrees it has to go through, and it takes a lot longer. So radians are faster. So graph it, and then that's it. So if I wanted to graph any of my polar functions, I can go in here and double check. So if I want to graph r squared, so say r squared equals 9 plus 2 theta. So I cannot do an r squared, so I'll have to do second square root, and then it's 9 cosine of 2 theta. But for this one, I need to make sure I also do a negative, because it'll only give me half of it. So negative second square root 9 cosine of 2 theta. And graph it. And hopefully you guys know I'm going to get a lemniscate. And it's still going. And here we go. Still graphing. There you go. There's your lemniscate. It was cosine, so it would go this way. And we're done. So use your calculator. It's actually still going. I'll show you something else once it stops. Still going. I guess I could stop it. It's done. I stopped it. To stop your graph, you hit second on it. It'll stop graphing. So if you go to your window, your theta min, theta max, x min, x max, x scale. Your scale is what you're looking at, or your step. Your step is going by 0.01 radians. So that's pretty good. It's going from 0 to 2 pi. And I could make it graph a little faster by going by like 0.1, and it should move faster. Yep, see, it went a lot faster. It's not as, the clarity of it's not as there as much because the steps are not as close. But if you want to make it graph a little faster, let's say I went to, 0 is fine there. If I went to 1, this is not going to be good. So it goes by 1. So really, I just got a few points there. So don't make it 1. 0.5, sorry, 0.05 is probably pretty good. Yeah, it's a little bit clearer. The 0.01 is really good, but it took forever to graph. All right, I hope that helps. Use your calculators to help guide you, figure out what the shapes look like before you graph them.